Let us begin. So I did a slight audible on what I had originally planned. Instead of, I was going to do some more set stuff, but I really want to just talk about some famous proofs and proof techniques, because that's kind of what this course is all about. But I wanted to introduce a couple of them before we get too far into the class. And there's like, I've said a few times that like, there's something about mathematical culture that you're also learning in this class, like what pure mathematics is all about. And there are some proofs that you just like have to know if you're going to be a math person. Like you're going to be expected at cocktail parties to be able to prove things. So people will demand it of you. No, or you'll start talking to people about proofs and they might be backing away slowly, but maybe before they finish backing away, you can impart some wisdom. And I want to talk about sort of like, especially since a couple of these are very famous, there's like it's like an old, like an archaic way that they were sort of explained it, and there's like the modern way that we actually try to be like super logical with, proofs. So here's a couple of famous proofs, famous propositions and slash proofs, So here's one. There are infinitely many primes. You've probably heard of this. You might have even seen the proof before. Or maybe this is a surprise to you. Maybe you thought the prime stopped after 19 or something. That was the last prime. But no, there's actually infinitely many primes. And I will say we're going to maybe make some assumptions in both of these proofs that I'm going to sort of assume unique prime factorization, because we're going to prove that eventually from axioms, but that's sort of like a given, right? So assume we can factor numbers into primes, or at least, actually for this one, you just have to say that every number is either prime or has a prime divisor, which is a little bit easier to prove, and we'll prove that at some point. So yeah, so assume unique prime factorization, meaning we can always factor numbers into primes. And we will prove this later. Okay, and so here's sort of like, by the way, this proof goes back to Euclid. So this is, a more than 2,000-year-old argument. And when I would say proof and like quotes, because they sort of had different standards for what was considered like rigorous logic, right? And so maybe the idea is like, basically I want to show, like what Euclid did is he showed like, if you have some primes, you can always make another prime, right? So given some primes, I can always like construct another one. And so that's a way of saying that it can't be a finite list, right? So so let P1, capitalizing that, P1, P2 through Pn be prime. Has anybody seen this argument before? Like how I can make another prime? In fact, maybe I should give some examples. Like if I start with just 2 and 3, here's a way to make another prime. Or let's do 2, 3, and 5. It makes it a little more interesting. Just like, so let's just say we have 2, 3, and 5, right? Here's a way to make another prime. Multiply those together. What do you get? 30. That's a multiple of 2, multiple of 3, and a multiple of 5. Add 1 to it. 31. Is that a multiple of 2? Is it a multiple of 3? Multiple of 5? No, when you add 1 to a multiple of 3, you get a non-multiple of 3, right? When you add 1 to a multiple of 5, you get a non-multiple of 5. So then 31 must either be prime or factorable into smaller numbers. And it turns out it's prime, but yeah. So that's kind of the idea. So consider capital P, which is P1, the product P1 through Pn plus 1. So the idea then is that just P is not a multiple of any of those P1 through Pn. because it's one more than a multiple. I mean, we're going to talk about divisibility, and we'll have like more sort of like concise ways to say this, but just in words, yeah, this number is not a multiple of any of P1 through Pn. So either P is prime or it is factorable into primes, different new primes. So either P is a new prime or is factorable into new primes. Oh, I meant to look this up, but there is a state, there is a point where if you keep doing this, you get a number that's not prime. Oh crap, I'm trying to remember now. It's like, if you do 2 times 3 times 5 times 7 times 11 plus 1, or maybe times 13 plus 1, you get a number that's actually not prime, but it factors into 2 primes that are bigger than those. Sorry, I meant to like look it up for class and I forgot. To new primes. So I mean, this is called like, maybe you could call this like infinite creation. Like you can always create new primes. It's not, maybe it's not a term. There's gonna be a term I'm gonna use in a minute called infinite descent, which is definitely a term that was used. So always more primes. Basically, you can never run out of primes. Right? Does that make sense? Yeah, so that was the argument. That's like the classical argument given by Euclid, or at least attributed to Euclid. So we don't have that much from, we don't have that much left over from those eras, so who knows, but yeah, okay. But if I want to make this a little bit more sort of rigorous and put it in the language we've been using, this is what we do, is we do what's called a proof by contradiction. Okay, and so I wanted to start showing you proofs by contradiction because we're going to use that a lot. So maybe modern proof by contradiction. And the idea is you sort of assume that what you're trying to prove is not true. Assume what you're trying to prove is not true, and then show that that leads to some sort of logical contradiction. And therefore, that was a bad assumption. Your assumption was wrong. Therefore, what you're trying to prove must have been true, right? So assume there are finitely many primes. So this is the same, it's going to be the exact same argument. It's just presented slightly differently. So you could even have the set of primes, you know, P1, P2 through Pn, right? So if it's finite, we can list them. And then the sort of same argument, right? I mean, again, I can probably be a little more rigorous about, in fact, maybe I should just go ahead and do an aside here on the divide symbol and divisibility. So, and this is on that properties of the integers handout. We say A divides B, and write the notation for this. It's a little bit weird, so it's another reason I want to go ahead and put it in. It's just a vertical bar, just A. So it's not A over B. You have to be a little bit careful, because A over B represents a different number, which is probably not an integer. But we're saying A vertical bar B, A divides B. If and only if there exists a K in Z, an integer K, such that A times K equals B. Right, that's what it means for one number to divide into another number. It's really like divide evenly. A divides B. So for example, 2 divides 6, right? So when you see that vertical bar, you just read it as a verb. 2 divides 6, but 6 does not divide 2. Just to like, it's the other way around, right? I'm not meaning a fraction 6 over 2 or anything like that. You can do this with any, 10 divides 1,000. 7 divides 91, and was 7 times 13. One interesting example here to think about is the number 0. Three divides 0 versus 0 divides 3. I say one of these is true and one of them is false. Which one is true? Yeah. Yeah, why? Right, so like what's the K in this case? 0, right? Yeah, so this is true. 3 times 0 equals 0. But if you try to do the same thing here, you have 0K equals 3, right? So this is false. There's no, 0 times K is, well, hey, we proved it, 0 times K is 0. Good, thanks. Okay, makes sense. So, it's kind of funny. Every number divides 0. 0 divides 0, but 0 doesn't divide anything else. So I just got to get used to this. There are some properties that are going to be useful here, like if, which we could prove later, but I don't want to go too far away from the proof of infinitely many primes, but a property of this symbol is that if A divides B and A divides C, then A divides B plus or minus C. It might be helpful to think also A divides B is the same thing as B is a multiple of A. So if B and C are multiples of A, do you agree that B plus C is also a multiple of A? Right, if you take 2 multiples of 5 and add them together, you still have multiple of 5. If you subtract them, you still have multiple of 5. Okay, so I think that's all we need for this proof. So in this side on divides. So we're going to consider, back to the proof, we're going to do the exact same thing, but I'm going to be a little more rigorous about it. Consider P equals, capital P is the product of all these guys plus 1. Claim, sometimes when we write proofs, we sort of can write like a claim in the middle of it, which is sort of like just a little subproof, like P1 does not divide capital P. Right? And this is almost, actually this claim, proving this claim is going to be almost like a little mini contradiction, which is basically, if it did, right? If so, P1 divides P and P1 divides this product, P1, P2 through Pn. So P1 divides that and it divides that. What would that also imply using this fact? Yeah. Yeah, so if it divides both of these, then it would also have to divide 1. Does that make sense? If this was a multiple of P1 and this is a multiple of P1, then that would also be a multiple of P1. So that's kind of way, again, we sort of said that earlier, but being a little more rigorous. So P1 divides 1. Well, we haven't proved that 1 doesn't factor in anything, but we can prove that axiomatically too at some point, but which can't be true. So that's almost a little That's sort of a mini contradiction proof, sort of like if assume it does, and then you get something that's has to be false, right? So similarly, none of the PI doesn't divide capital P for all I, right? But P does have a prime divisor, you know, like either it's itself is prime or, yeah. But by unique prime factorization, there exists Q prime in Z such that Q divides P, capital P. And I'll just say aside, maybe Q equals P itself, right? But you don't really have to separate that as a case. It's sort of contained in. I guess maybe one thing I should have set up here is that when I listed that set S, P1 through Pn, that was supposed to be all of them. Instead of all primes. Right. Okay. And so what we've just shown, if you think about it, is we've shown Q is prime, but Q is not in S. There exists a prime Q. There exists a number Q that is prime, but not in S. And that's what your contradiction is, if S is supposed to be a set of all primes. Right. Q is prime, but, oh, I should have said Q is not equal to any of these, right? Like, I should have said first. Q, by this comment, Q is not equal to PI for any I. Right, because you can't have Q divides P and Q doesn't divide P at the same time. So Q is prime, but Q is not in S. And that's a contradiction. Because S was supposed to be the set of all primes. Does that make sense? You can sort of see why the archaic way is a little more charming, because this is kind of, we're getting very like detailed and very like having to mind all our P's and Q's. Yeah, like the idea is still in there, but we're just being a little more rigorous about it. By the way, there's different notations for contradiction. Some people use like, I guess it's supposed to be like two arrows hitting each other. I kind of like the two implies arrows hitting each other. Like they're kind of butting heads. There's something I've seen with like a weird squiggle with a line through it or something. But you can also just write the word contradiction, or this is a contradiction. And so our assumption was faulty. Thus, our assumption was wrong. And our assumption was that there are only finitely many primes. So that's the idea of a proof by contradiction. We assume there are finitely many primes. We derive some sort of logical contradiction. I mean, this is kind of a weird proof, because we kind of contradicted the list of primes, which is very direct. Sometimes you contradict something that's more indirect. Because if you can reach any logical contradiction, then you've obviously made some bad assumption, right? Therefore, there are infinitely many primes. That's another reason I like LaTeX, because it's much easier to just like type all that out nicely and quickly, just, you know. And that's the end of the proof. Okay. Fair enough. I mean, there's some stuff rigorously you might think about, like why this can't be true. We didn't really prove that. Everything else, I think, is. Any questions about that? Yeah, so this is a famous proof. There are other proofs. There's a lot of proofs, infinite, why there's infinitely many primes, and some of them are nice. There's a proof using the harmonic series that I particularly like. That the sum of 1 over n. That the fact that that diverges is actually equivalent to the fact that there's infinitely many primes, which is weird. But maybe I'll show you that sometime later. There's actually a book, which it's on my shelf and I sort of meant to bring it down the hall, but called Proofs from the Book. And there's this idea that like, there's a book that God writes all the most beautiful proofs in. And that if you find a particularly beautiful proof, like particularly beautiful and elegant proof, you can say it's a proof from the book. And again, more math culture. There was this guy named Paul Erdős, who now died like 20 years ago, but he was a very famous mathematician in the second half of the 20th century. He was effectively homeless. He just had a suitcase and he would invite himself to mathematicians' homes and live with them for like a month and work on them work on a problem with them. And then they'd like write a paper and then he'd like move on to someone else. So he just, his whole life was, that's all he did was math. His whole life, he didn't have a place to live or anything. You know, he just basically was like, you feed and house me and then I'll do math with you. And he's a famously prolific guy. He wrote like hundreds and hundreds and hundreds of papers in his life. And then if you collaborate, then people have an Erdős number, which is if you collaborate, if you wrote a paper with Erdős, your Erdős number is 1. If you wrote a paper with someone who wrote a paper with Erdős, your Erdős number is 2. I guess if you are Erdős, your Erdős number is 0. And so on. I think my Erdős number is 4 last time I checked. Not that great. Can't be 1 anymore since he died, sadly. But but he's the one who came up with the idea of the proofs from the book. He would always talk about proofs from the book. He also famously did lots and lots of amphetamines. Did a lot of speed to do, so he could do math all the time. There you go, right? I recommend it. No, I don't. I'm not saying. I mean, Adderall is basically speed, right? All right. Yes, Laura.
I realize I do have a question.
Good.
And this might be really rudimentary, but
No.
There's the claim, like you want the p divided by 1, and then how do we get to the next line? So we want.
Oh, maybe I should say if not or something. Yeah, you're right. Maybe I should have said if not there. Yeah, thank you. Yeah, it was too imprecise. In my head, I was like, if it does, so that's like a positive thing. So if so, you know, but you're right, you're right. So if not, we have P1 divides P and P1 divides. Yeah, good, thank you. That's good. Yeah, and I mean, this is the end of the claim right here. It's just kind of a little, sometimes people put a little mini, like it's a little mini proof or something. Good. No, that's good. That's also partly I was filibustering. Hopefully somebody would find something to ask a question about. All right, so that is that proof. Let me give you, let's do another, should we do another famous proof? Let's do another famous proof. That's also going to somehow depend on unique prime factorization. Well, I won't even say that here because the archaic version, which goes back at least to like the 1600s, is I don't even think quotes unique prime factorization really. I mean, it sort of does, but so here's a famous fact. The square root of 2 is not rational, it's irrational. Like, how do you actually prove that? How do you prove there's no fraction? So we can say it this way, the square root of 2 is not rational. not in Q. It's not equal to A over B for any fraction A over B. This is actually something that deeply disturbed the Greeks. They did all these sort of geometric constructions, and they could get root 2 as like the hypotenuse of a, right isosceles triangle 1 and 1. And they wanted to, but they didn't know really about irrational numbers, so they were trying to figure out for a long time, like, okay, we can construct this thing, hypotenuse of a 45-degree, right isosceles triangle. Why can't we figure out what it's equal to? And I think there was even, there's all these stories out of like the Pythagorean school that it was kind of a cult, and that if you like went against the teachings of the cult, you could get killed and stuff. So like they didn't want to like allow the existence of irrational numbers. So then it was like this whole thing of like, we can't show this as rational. Maybe it's not. Let's keep it a secret. If you say anything about school, we'll kill you. That's when math had stakes, right? So again, the archaic proof, which goes back at least to like Fermat in the 1600s. Again, quote proof, because it uses something that's not that. This is even going to be even more like sort of clearly not rigorous, which is, but it's a proof by contradiction. So assume it is. Assume root 2 is rational, i.e. root 2 equals A over B for some integers, for some A over B. It's for some A and B in the integers, right? Okay. Has anybody seen this proof before? Oh, good. I'm imparting culture to you. That's very important. Okay. Well, I'm saying that because times in the past I've taught this class and not really focused on like, oh, there are some proofs that everyone should see. And I might have like not even ever proved this, which is unforgivable, really. So you guys get the benefit of my earlier mistakes. So, okay. One thing you can start to do if you want to play with stuff involving the integers is you could square both sides and move the b squared over and make it a statement about integers, right? So then 2 is a squared over b squared. And that implies a squared equals 2b squared. What does that imply about A? Can you tell me anything about A? Knowing that A squared is 2b squared. Very vague question. Think about parity, even and odds. A has to be even, right? So if A squared is even, then A is even, which is something we could probably prove. But let's just go with it for now. So A squared is even implies A is even, which implies A equals 2k for some k in Z. And if we plug that in, we get 2k quantity squared equals 2b squared. And if you just think about that, what does that become? 4k squared equals 2b squared, and b squared equals 2k squared. Right? What does it tell us about b? B is even, right? So b is even. Okay, let's write that down. So b is 2l for some l. B squared even implies b even, implies v equals 2l for some l, some integer l. Okay, plug that in. 2l quantity squared is 2 k squared. Which leads to k squared equals 2l squared. Can you simplify? What does that mean? K is even. So k is even. So k is even. K equals 2m. Okay. Do you see where I'm going with this? L is even. And you can keep going forever with this. You can keep pulling out 2's forever. If this is true, right? So keep pulling out 2's forever. This is what Fermat or other people would call an infinite descent. And you're basically saying that if you're in the integers, an infinite descent is not possible. We can't take an integer and factor 2's out of it forever. And it will remain an integer, right? There's only so many, there's only so many 2's you can have inside an integer. So infinite descent, which like to Fermat was a contradiction. Descent, contradiction. So this is how they would write things. Like basically, if they could construct an infinite descent, or like up there, I call that like an infinite, what did I call it? Like an infinite creation or something. Nobody uses the term infinite creation. I think I just made that up, but lots of people use the term infinite descent. So infinite descent, contradiction. Therefore, oh, I don't know if I've said the 3 dots is kind of, that's also a therefore. Again, when you're typing out math, just type the word therefore. But when you're writing something by hand and you're trying to do it quick, yeah, this 3 dots in a triangle is a therefore symbol. So the contradiction, so we assumed root 2 was rational, so therefore root 2 is irrational. Okay. So that's the that's the sort of like the classical, maybe archaic's a little mean. Maybe I should have said classical proof. Classical is a nicer word than archaic. So yeah, you can sort of cast out 2's forever or whatever. So there's lots of arguments that are infinite descents. If you go back and read, like, Fermat and Euler and people in like the 16 and 1700s, and you get lots of infinite descents. Okay. So now the question is, how do we make that a little more rigorous? Because saying I can't pull out 2's forever does not really seem like something. It's not something you can like grab your hands on that concretely as like, like if you think about the stuff we've done with like truth tables and sets, that's all very like boom, 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 logic, logic, logic. There you go, and even like this few proofs you've done about the integers of like just use the axioms and logical inference, So how can I make this a little more modern? Well, the idea here is, again, to use unique prime factorization and say, basically, I mean, there's a statement that we haven't proved yet, but I think it's going to be believable, that you can write A over B already in lowest terms. You can write a fraction. You can always cancel anything common and get like, so that the top and bottom don't share any common factors. And that really does come from something like unique prime factorization, the fact that you can do that. It's really the idea that there's something called a greatest common divisor. And we're going to talk about GCDs at some point also, like rigorously, but basically A and B, if you write a fraction, A and B have a GCD, which you could pull out and cancel, and then get a fraction that has no common factors in it. Okay, and so what we're doing is, instead of making an infinite descent, we're making a descent where we get a contradiction at the first step. Because once we show that 2 is in both of them, that contradicts the idea that they were supposed to start out with no common factors. Does that make sense? So that's really the more modern construction sort of is to like somehow take an infinite descent and make it something that is contradiction at the first step instead. You could argue it's just a way of reorganizing the logic or something, but it's, to me, it feels a little more rigorous. So, let's use, well, okay, let me just say, again, assume square root of 2 is rational. And you can, I just want to say you can use unique prime factorization. I'm going to start writing UPF for unique prime factorization often because I'm going to use it a lot. I don't want to write it a lot on the board. And the notion of GCDs. Greatest common divisor. To say that we can write root 2 is A over B, but with the additional conclusion that where the GCD of A and B is 1. So there's no common factors. Right. And again, this is stuff, once we start talking about this, we can prove these from the axioms that this is possible. No common factors. There's a term for this, which I might as well go ahead and tell you. A and B are called relatively prime. So they're not, they're not necessarily prime numbers themselves, but they're sort of prime to each other. They don't share any common factors. That's a term that'll come up a lot. Yeah, two numbers whose GCD is 1 are often called relative or co-prime. So you see co-prime also in books, relatively prime or co-prime. Okay, so we're going to assume there's no common divisors, right? There's like no, yeah. Okay. And so here's exactly what we're going to contradict if you just think about the proof already, right? This is what we're going to contradict right here. Because we're going to show there's a common factor. And I don't know how you feel about whether this is like more satisfying or less satisfying, but infinite descents always seemed a little shady to me. It's like, I don't know, if they were rational numbers, you could pull out 2s forever. But okay, so then it's the same argument basically. Root 2 equals A over B implies 2 equals A squared over B squared. Implies A squared equals 2B squared. Which implies A squared is even. Which implies A is even. And we could talk about proving this. I think the book's first example of a proof by contradiction is like that if A squared is odd, then A is odd. Because if not, if A is even, then you can show A squared is even, which contradicts A squared having been odd, So A is even. So that's kind of the argument. And then I'm just going to go through the same stuff, but as soon as I get the B being even also, then that's going to be the contradiction. I don't have to do the fun, like, let's just keep pulling 2s out until we get bored and decide that's not possible. So A equals 2K for some K. Copying the same ideas, that's why I'm maybe a little more terse even. Plug in 2K squared equals 2B squared. So just a lot of implications, right? That implies B squared is even, which implies B is even, which implies B equals 2L for some L. And that implies that, so now we have that 2 divides A and 2 divides B. 2 divides A, 2 divides B, but the GCD of A and B is supposed to be 1. And that's a contradiction. Yeah. And therefore, the assumption was wrong. So root 2 is not. Okay. All right. Good. Now you know the piece frames proofs. You can go spread them far and wide. Just want a break for a couple minutes. Last other classes. So we're not going to really do group work today. I know if I talk for 85 minutes, it's kind of straight. It's kind of a little bit tedious. Let me pause the recording. And let me share screen. Share this. So, right, so we had these axioms. And I was talking about the 7th axiom last time. The Z is ordered axiom about this special subset, how we define the positive numbers and living inside the integers. By the way, the well-ordering axiom, which we will talk about soon, uses lots of proofs by contradiction because like you sort of like construct subsets of the natural numbers that don't have smallest elements or something, and that contradicts something, and you know that's so we'll see that. But remember, the ordering axiom says basically we have this special subset. The things to remember about it is that it's not empty. We have closure, and we have this trichotomy, right? And every integer either lives in that set, is 0, or its additive inverse lives in that set. And so if you want to try to do things axiomatically, that's the non-empty actually will become important at one point. I think I said the set just 0 satisfies axioms 0 through 7 if you don't say that there is a non-empty subset. So if the positive numbers are empty. So, and then we have this properties page I shared, and we have some, let's see, we have some, so there's the divisibility, right? There's the divide symbol. There's a few things here, like you've proved 1, 2, and 3. We've proved 1, 2, and 3. I'm actually gonna talk briefly about 4 and 5. And then here's stuff about the divide symbol, which is this definition we just gave. And you can imagine, right, we sort of mentioned this, that if A divides B and A divides C, then A divides B plus C. You can imagine there's some sort of transitive thing. If A divides B and B divides C, then A divides C. And we'll talk about some of these other properties. But that's how you get into the notion of GCDs and stuff, is like looking carefully at what the divide symbol means. And then we have this ordering, right, given that we say, now that we have the natural numbers, we say A is greater than B if basically you can add a natural number to B to get A. So, you know, some people would also give the definition just like A minus B is positive, is a natural number. That's another definition you can do. This one's a little cleaner, it's a little nicer for various proofs. And the thing I really want to prove today is I want to prove that 1's greater than 0, which seems like a really ridiculous thing to prove. And then on the problem set is this which is very similar, which is not quite closure. It basically says if A and B are positive, then K also has to be positive. So it's not the same thing as saying a positive times positive is positive. It's saying if you have a positive times an unspecified number and you get a positive number, then that unspecified number must have been positive. Fair? Okay. So, all right, so let's just jump back into this a little bit. I do want to, just as an aside, and because actually there's a place on the problem set where you can use uniqueness of additive inverses. I just want to mention why those are true. So let's go back to axiomatic number theory. maybe we might not get to induction today, but that's okay. It's not on the problem set for next week, so we can do it. We can start induction Tuesday probably. So back to axiomatic number theory. But we're also going to do at least one proof by contradiction here. So this will also illustrate the idea from earlier. So so first, the idea of uniqueness is important. It's a thing that comes up in a lot in mathematics. Is we talk about existence, like whether there exists a number that does something or there exists a solution to something. Like if you take differential equations. Anybody taken 2208? Because it's like, no, this isn't a prerequisite for it. No. You talk, if you have like a differential equation, there's like theorems about existence of solutions, but there's also theorems about uniqueness of solutions, that you have a solution, there's one and only one solution. So existence is almost like at least one, and uniqueness is kind of at most one, right? Versus existence. This is like, yeah, this is like at least one. And this is like at most one. Sometimes when you prove, when you prove uniqueness, sometimes you're not actually proving existence. So you're kind of proving if it exists, it's unique, you know. And so if we say something exists uniquely, that means there's exactly one, right? There's actually a notation for this. If we want to say there's a unique, like, so notation is there exists exclamation point. It's just kind of a random notation, but that's like there exists a unique. And so we could have stated the additive identity and inverse axioms as uniqueness. We could have said there exists a unique integer called 0, so that a plus 0 equals a. But I claim you can actually prove it. If you just assume that, if you just say that assume it exists, you can actually prove that it's unique. So here's a proposition. The additive identity is unique. Now this is interesting because we could state this as a contradiction proof. We could say, assume there's two different ones, right? Assume we have two additive identities, and I can sort of derive a contradiction. But the contradiction I'm going to derive is that they're in fact equal to each other, which kind of says they weren't different in the first place. So in some ways, what I would just rather do is say, let 0 and 0 prime both be additive identities. And I'm not just saying whether they're different or not. So if you say they're not equal, then you're doing a proof by contradiction, because you're gonna actually prove they are equal. But you can organize logic, just don't say anything about it and prove they're equal. And that is another way of proving that it's unique, right? By picking any two additive identities, they're actually equal to each other. Okay, what does it mean to be an additive identity? What's the definition? What's the axiomatic definition of being an additive identity? Yeah, super. Yeah, so we can say a plus 0 equals a, and a plus 0 prime equals a for any a. Right, and then what are you tempted to do now? I'm trying to show 0 equals 0 prime. Can anybody guess? Yeah. Yeah, we can, this equals and this equals means that we really have a plus 0 equals a plus 0 prime. So, and I sort of said, like, you know, you can use these properties of equality without comment. I mean, you could sort of like, there's a symmetric property of equality, which means you can flip these, and then you can, transitive property of equality means you can chain them together. But let's just, there's a point that we don't want to go below, right? So let's just use this. So then a plus 0 equals a plus 0 prime. And then what do we have? It's actually on the properties page. I mean, I could sort of start adding negative a to both sides and stuff and canceling, but we have it, right? We already have number 1 on the screen there, which is we can just cancel. Then by cancellation of addition, zero equals 0 prime, right? So it's kind of silly, but it's a proof. It's like we want to say there's only one unique additive identity. By the way, there is a slightly slicker proof that I sort of like, which is let a 0 and 0 prime both be additive identities. Consider 0 plus 0 prime. What does 0 plus 0 prime equal? Yeah. Right. So if you yeah, like I won't write this proof down, but like if you just think about this, if you're treating 0 as an identity, then this equals 0 prime. If you're treating 0 prime as the identity, then this equals 0. And so you get 0 equals 0 plus 0 prime equals 0 prime. Kind of a slick proof, but this is kind of the more straightforward proof. And there's a similar proof for uniqueness of additive inverses. You could imagine that if negative a and negative a quantity prime were two different additive inverses, that you could do something, you would have something very similar. Or you can consider, another slick proof is to consider negative a plus negative a prime. If you collapse this, you get negative a prime. If you collapse this, you get negative a. So they have to equal each other. So I'm not going to prove that, but I will say, oh, there's something I asked you to prove on the homework that like, I asked you to prove on the homework that like negative a times b is negative ab is a times negative b, that these are all the same. Which you could do, oh, you know what, I just realized you could do by making these negative 1 times a and just using associative parentheses. But I don't want you to do that. I want you to, sorry, I should say that, I guess. That's the lame proof. The better proof is like, this is the additive inverse of AB. So show that this is an additive inverse of AB. If you show that if you add AB to this and you get 0, then this has to equal this by uniqueness. Does that make sense? A little bit weird. But like this is the additive inverse of AB. So if this also acts like an additive inverse of AB, then it has to equal this. Sorry, I'll try to put a comment on there. Don't do the lame proof of just making this negative 1 times a and then moving parentheses there. You could do that, but I kind of like the more direct. Okay, so I won't write down the proof of unique additive inverses, but you can sort of guess. Okay. Okay, so then back to ordering properties. Again, the things about, let me just write this on the screen, on the board real fast. So ordering, there exists, it turns out it's unique actually. You can prove that it's unique. It's not really part of the axiom, but there's a unique subset of the natural numbers such that, I guess I could almost do 3 bullet points. N is not empty. A and B in the natural numbers implies A plus B and A times B is in the natural numbers. And for all A in the integers, either A is a natural number, A equals 0, or negative A is a natural number. Thanks. Right, those are the 3. And then we defined A less than B. I could define A greater than B, A greater than B. And then we do I'm just doing these shorthand of A equals B plus K for some natural number K, for some positive number K. Okay, we've written these down before. I just want to write them down again. What was I was talking with my linear algebra class about suffering. We were writing out just horrible like matrix things over and over again. My hand was getting tired and I was like, you have to be willing in math, this form of suffering is write stuff over and over again until it's just like embedded in your hand. It's like muscle memory, writing stuff down. So we've written this down a couple times now, but okay, so I want to prove 1 is greater than 0, right? That's the thing I want to prove. Before I do that, I do want to prove number 13 up there, which seems like a dumb thing to say, but A is greater than 0 if and only if A is a natural number. Because we define the natural numbers as a special set. We define the greater than symbol in terms of the natural numbers. And so I want to really say that positive means lives in the natural numbers. Right, like greater than 0 means positive. You can almost call this what's called a lemma, which is like a little smaller proof. Sometimes the word lemma is used for like a smaller proof that just helps you with other proofs. So I'm going to call this maybe a lemma. It's like a funny thing of like whether you want to say it graduates to the level of a proposition or like an important true statement is called a theorem. Sort of a true statement that's maybe not as important, you know, you could call a proposition something that's just auxiliary that helps you prove other stuff's called a lemma. So there's also, and then there's also the word, yeah, there's like lemma, proposition. Again, this is all just cultural things and you can just decide for yourself what you want to count. There's also corollary, which is something that follows immediately from something else. It's called a corollary. Like if I prove something and then like in one line, I can sort of say that proves something else. And that's often called a corollary. So those are just terms that are used. Okay, so lemma, A is a natural number, or let me just say A is greater than 0 if and only if A is a natural number. And one reason I want to prove this, besides that fact that it's useful and it shows how the definition works, is it's an if and only if. So I need to prove left implies right and right implies left. And so often what we do is, because this is really like an if and only if, this is really like a double-headed, which means right, that's what that means, that I want to prove left implies right and right implies left. And so often when we write proofs, we'll do something like this. Let's like, I'm just going to prove this direction. That's like a, and then lower down, I'll have the opposite, going in the opposite direction, right? So if A is greater than 0, well, we have a definition, right? That means there exists a K in the natural numbers such that A equals 0 plus K. You starting to believe that A is a natural number? So really A equals K. Therefore A equals K, which is in the natural numbers. So A is in the natural numbers. Okay, that was easy. That's why it's a lemma. Easy to prove one direction. The other direction, well, again, it's also very short and easy, but it's A is a natural number. I want to prove A is greater than 0. So I want A equals 0 plus something. That's a natural number. Forget about everything we did before. What is A equals 0 plus something that's a natural number? A equals 0 plus A. A equals 0 plus A. It's kind of the backwards version of this, but A equals 0 plus A by the additive identity, and then by the definition of greater than, A is greater than 0 because, A is greater than 0 because A is a natural number. Right, it's kind of silly, but it's like A is supposed to be 0 plus a natural number. And I just evidenced it. I mean, you could almost make this just if and only ifs, but it seems a little weird to go from A equals another letter to that, you know. So I just did it both ways. Okay. Okay. I had thought about proving 14. I think you have to do 15 on the homework. 14 is pretty straightforward, but I really want to prove 17. I want to prove that 1 is greater than 0. So that's more interesting. So you might think about how you can do 13, just that you can add an integer to both sides of an inequality and it stays an inequality. Okay, so here is a proposition that I want to use. I guess maybe this class is really about the proofs by contradiction, because we're definitely going to do proof by contradiction. This. So the claim, so the proposition is that 1 is greater than 0. Which we could also just say by what we just proved, or we want to, either way, or we want to prove 1's a natural. 1's actually lives in the set of positive integers. By the way, you might think this is really stupid, but 1 is not 1. 1 is the multiplicative identity. Right? You know 1 is 1 because you're used to 1, but like, to say the multiplicative identity is positive is like not an obvious, or that the multiplicative identity lives in this set natural numbers is not like, I think it's less obvious when you say it that way. There's even a, like an even more obvious, not obvious thing here. There's no integer between 0 and 1. Again, that seems like completely obvious with our experience. But if you say there's no integer between the additive identity and the multiplicative identity, that seems less obvious. If you sort of abstract away what 0 and 1 actually mean. Everything in our experience tells us there's no integers between them, but we will actually prove it next week sometime. So, okay, so here's the idea. Here's the idea of the proof. So, and I am sort of doing something bad, which is I'm just going right into the proof rather than just doing like ideas and scratch and stuff. Partly is only we only have 10 minutes left, and partly it's like I'm going to give you just like what the structure of the proof is. We have, if you look at the top right there, we have the trichotomy thing. And if I plug 1 in for A, right? By trichotomy, either 1 is a natural number, or 1 equals 0, or -1 is a natural number. What I want to do is show that these two cases both lead to contradictions. If these two cases both lead to contradictions, then we're just left with that, right? That's why we can sort of, that's one reason trichotomy is useful. Every integer has to fall into one of these 3 categories. Yeah. Okay, so again, if you want to do it as a proof by contradiction, you could say assume 1 is not a natural number. And that means either 1 equals 0 or -1 is a natural number, and then you could do 2 cases. So assume 1 is not a natural number. Then we have 2 cases. And I talked to some of you guys about proofs by cases. Like, I talked to some people in office hours last week about like, if you have A union B, then you could break it into 2 cases, like X is in A or X is in B, and you could just do 2 separate cases rather than try to do a bunch of formal nonsense with like logical equivalences and stuff. Sometimes it's just nicer. And here you really have to break it into 2 cases because they're just completely separate cases. Let's show each leads to a contradiction. Okay. And they're going to lead to contradictions because they definitely feel wrong, right? 1 equals 0 feels wrong. Or maybe I should just say, suppose 1 equals 0. Why is that wrong to you? If 1 equals 0, what else equals 0? Yeah. So you want to multiply both sides of this by a. And then on the one hand, you get a, on the other hand, you get 0. So if 1 equals 0, then everything is 0, is what you're saying. Yeah. I was going to say, like, if 1 is 0, then 1 plus 1 is 0, so 2 is 0, so 3 is 0, so 4 is 0. And yeah, same idea. You can sort of collapse everything down to 0. What in the axioms, I've mentioned this already, what in the axioms tells us that not everything collapses down to 0? What did I say? You guys remember? How do we know the integers is not just the set containing 0? Said something. Yeah, you remember? Well, it said every non-empty subset has a smallest number, but we don't know that that there is a non-empty subset. It's on the board up there. What does it say? What's proposition part 0 of the ordering? N is non-empty, right? And if you think about the first 0, 0.0 up there and 0.2 up there, if n is non-empty, then that means there's some non-zero integer, right? Because there's an element of n and it can't be equal to 0 because of trichotomy, right? So n is non-empty. I mean, this is sort of important because otherwise 1 equals 0, there's nothing wrong with it. So select a in the natural numbers, right? But then it's exactly your argument, basically. Let's just multiply both sides by a. Yeah. A times 1 equals a times 0. But that by the additive identity, that's the left-hand side is just a, and because we proved a times 0 equals 0, we know that the right-hand side is 0, right? But do you see how we can't have both of these at the same time? Because that contradicts trichotomy. This contradicts trichotomy, but this contradicts trichotomy. But a in natural numbers and a equals 0 contradicts trichotomy. Okay, so that's a contradiction. Now the other case is if -1 is a natural number. Well, since we only have 3 minutes left, I might sort of give you the punchline, which is that, so we can do something very similar to what Colin suggested, which is let's consider multiplying this -1 by an a. I mean, the thing is if -1's positive, then if a is positive, -a should still be positive. Well, let me just, again, we're going to run out of time. So again, pick an a in the natural numbers. And consider -1 times a. On the one hand, we have closure, right? If this is a natural number and this is a natural number, then the product is a natural number. on the one hand, closure of the natural numbers under multiplication implies -1 times a is a natural number. But what does -1 times a equal? You proved it. -a. So, but on the other hand, -1 times a, I don't know why I said the other hand, it's really just, I don't know why I'm saying on the one hand, on the other hand, these aren't really opposite things, but so -a is in the natural numbers. So basically, we did the same thing, except now we have a and -a both in the natural numbers. Yeah, Adi. Yeah, but except we don't know that a natural number times a non-natural number is not a natural number. Right, we haven't proved that. You're right. Like if we proved a natural number times a non-natural number, like this doesn't say, like closure doesn't imply that. It doesn't mean if you could have something in the set and something not in the set, they couldn't, the product couldn't be in the set. That's interesting though. But yeah, I think this is, so then again, this contradicts. But a is an n, -a in n also contradicts trichotomy. And basically, since we got contradictions in both of those other two cases, we're left with where we have a contradiction overall. So therefore, one is a natural number, sort of below everything else. Okay, yeah. These are exclusive ORs. Yeah, I think I mentioned that last time. Like these are actually, this is exact, the way the axiom stated on the sheet is exactly one of the following is true. But yeah, you're right. I should have like an XOR there, really, sort of, if I wanted to be a little more formal. Good, thank you. Yeah, so you might like look back at this and think about it again, because it's kind of a strange proof. But we proved 1 is greater than 0, guys. Tell your parents you're getting your money's worth. Your college education. All right, we're done. It's actually 11:28, but we're clock up there says 11:30, so we'll stop there. All right.